So in this quick MATLAB example, we're going to look at how we can use inner products to do a detection between different waveforms that are transmitted in a digital communication system in order to tell if a 0 bit was sent or a 1 bit was sent. So very simply, we're just setting up two signals. Let's set up the signals and then plot them. Here are two signals. The first signal is basically a discrete time square pulse, and the second signal is two square pulses, one with positive entries and the other with negative entries. It should be clear from inspection here that signal x0 is orthogonal to x1, right? So that it turns out that's very convenient in a communication system. So now what we're going to do is we're going to corrupt. We're going to corrupt one of these signals. In this case, we're going to corrupt x0, which is up here, with a additive white Gaussian noise to obtain the signal here at the bottom. And you can see that this is an extremely noisy signal. If you compare the amplitudes here, it's extremely noisy. And this is an example of a signal that you might receive at the end of some communication system. And now the question is, was this signal what was transmitted or this signal? And the way that we determine which is which is very simple. We're just going to compute the inner product between these two signals and the inner product between these two signals, and then we're going to choose the larger of the two as the decision of which whether a 0-bit or a 1-bit was transmitted. And so let's look at that here at the bottom. We're just going to compute the inner product here between y and x0, y and x1. Okay, and you can see now, but looking at the two inner products, that the inner product of y with x0 is quite large, whereas the inner product of y with x1 is quite a bit smaller, and therefore we would determine that in fact a 0-bit was sent. So now we can basically repeat this experiment over and over so that you can see that, well actually let's just change to the 1 signal and let's perform the same example. And now you can see that when we compare the inner product between the received signal and x0, we get a very small number. And when we compute the inner product between x1 and the received signal, we get a very large inner product. So in this case, we would say that a bit 1 was transmitted, right? Moreover, since we have normalized the signals, you see that here we've divided out by their 2 norm. We know that the smallest that this inner product can be, notice we're taking the absolute value, the smallest it can be is 0, and the largest it can be is 1. And so we see that here we're doing really quite well. We have really an inner product that is 0.9344, which is about as close to 1 as you should expect to get with this large amount of noise. So now let's just, we can perform this experiment repeatedly. And basically, you just by watching these numbers here, you can basically see that the 1-bit is always, because we selected y as x1 plus the noise, the 1-bit is always going to be victorious. Oops. There we go. Oops. So there we go. And we see we have a slightly smaller value, but still the 0 bit is always winning out over the 1 bit rather is always winning out over the 0 bit, which means we can have quite a reliable communication using this technique. And just in way of wrapping up, we'll come back to this later, but this idea is called, the matched filter. Okay, let's go back to the development.